Hello everyone, it's Mr. Wolfe here, and in this video I'm going to be introducing proportional reasoning when it has to do with changing motion. So this is going to actually be on page 49 of our physics packets, all right? And this is going to be question number 4. So I'm going to show this example for a specific reason. So you are running an experiment where you let a bowling ball accelerate down a ramp from rest. So we can almost like draw a picture of this ball going down a ramp from rest in the SHS hallway. However, you pick up the ball only after 2 seconds because your friend was on Snapchat when she was supposed to take data. The ball only travels 3.5 meters. If you redo the experiment but let the ball run for 4 times more the time, what distance does the ball cover? All right. So what I want to do is I want to attempt to solve this mathematically first. All right, like if we were doing LT5A. So if I look at my givens, let's see, I have my initial velocity is 0 meters per second because I'd started from rest. My acceleration, it says it accelerates, but I don't know the acceleration. There's no units that say meters per second square. My time is 2 seconds, and it travels for 3.5 meters, so that's my distance. Right? So if I look at my equations, let's see, if I could bring up page. If I look at my equations, the only equation that has change in distance that has to do with changing motion is this one. This one has change in distance, but notice it's going at a constant speed. For my changing speed equation, I would have to use this one. So I'll flip back over. And I would use delta x is equal to 1/2 at squared plus my initial velocity times time. All right, so I'm going to start plugging in values. And keep in mind, I'm looking for the distance the ball would cover. All right, if I increase my time by a factor of 4. So my original time was 2. So what I could do is I could maybe put in 8 here, all right, squared, 1/2 a. Keep in mind, I knew my distance before, but I'm trying to see how much my distance changes if I change my time. So I'm solving for distance. And my initial velocity is 0. And again, my time is 8. All right, so there's the setup to my equation. Here's the only problem is that I can't solve for distance if I don't have acceleration. And it's not in this problem, and this isn't one of those things where I could use like any types of physics concepts to figure it out. So I cannot solve this problem the normal way. What I'm going to have to do is I'm going to have to do proportional reasoning. So in terms of the equation I'm going to use, first it's always important, and we kind of already did this, to think, is this going at a changing or a constant velocity? And since I'm accelerating, that literally means changing velocity. So this is a changing velocity problem. And as we talked about, this is the only equation that has distance in it, right? The other one, v equals at plus initial velocity, doesn't. So that's why I can't use that equation in this case. So I'm going to write down my equation. Delta x, I'll make a little bit more room for it, is equal to 1/2 at squared plus initial velocity times time. Now another thing I want to do is maybe towards the side somewhere, I want to highlight what my real values are. So that's anything with the unit. So 3.5 meters, right, and 2 seconds. All right, and I'm going to say that these are actual values. And what you want to do is maybe draw a line or something that kind of separates them from what we're about to solve. So we want to keep these values in mind possibly, but we don't want to use them right now. Right? So then I have my equation, and now I'm going to substitute, right, using that one-to-one method. So delta x equals 1/2. I'm just going to rewrite my equation because it's going to be a lot easier to show you how I'm substituting my variables. Right? So in this case, it says that, okay, what if we increase the time by a factor of 4? I'm going to put a 4 in, and that's squared. All right, my initial velocity, I'm not going to put in a 1 here because my initial velocity was 0. All right, so we'll literally just put in a 0 here. The time, again, is increasing by a factor of 4, so I'm going to put 4 in. Right? And then my acceleration, well, if it's the same ramp, right, it's going to be, like the gravity's going to be pulling it down at this specific angle with the exact same acceleration. So my acceleration is going to be 1. Right? And then I'm solving for my change in distance. Now, what about this 1/2? So the reason why I wanted to use this as an example is this is a really important rule. So if you head to page 5 of your packet, it talks about these things called constants. Right? So a constant are numbers in an equation that will never change. Right? And because proportional reasoning involves examining numbers that have the potential to change, constants should not be included when doing the one-to-one method. So an example of a constant would be like 1/2 v squared or 22ab, right? This g could be anything. It could be 1,000,000, 5, 7, right? I could put in any variable here. Same thing with a and b, but this 22 is never going to change in my equation. So here's an example. If I were to do proportional reasoning with it, right, and maybe a did not change, so it's 1, and b changed by a factor of 4, and I was trying to see how my g value changed, notice that I completely ignore the 22 as I do proportional reasoning, right? And that will give you an accurate answer. If I put my 22 in here, that would give me a completely different answer, right? 22 times 4, that would give me 88, which is way different than this 4 times as much right here. All right, so if we go back to page 49, we go back to page 49, this 1/2 right here, I don't care about this at all. It's a constant, I'm not gonna use it. So this is actually everything I need to do right here. All right? Now notice that 0 times 4 is just gonna be 0. So really what my equation ends up being is just 1, my acceleration, which hasn't changed, times my time, which changed by a factor of 4. But notice that this 4 is squared. So what I end up getting for my factor of change is delta x is equal to 16. Right? So this is interesting. We increase the time, right, 4 times as much. And in the past, like in our constant velocity unit, if something doubled, well, either it was like halved or it was also doubled. But in this case, since things are squared in my equation, right, time increases by 4, and the distance actually increases way more. It increases exponentially. Right? So my change in distance is going to be 16 times greater than before. All right. So now I have to apply that factor of change. And remember, the whole goal of this is what distance does the ball cover? So I'm not going to use my 2 seconds because that's time, but this was my original distance. So I'm going to take my original distance, I'm going to multiply it by the factor, 16, and that's going to give me a new distance of 56 meters. Right? So hopefully this example of proportional reasoning was helpful. Right, it's a little bit different where now we really have to choose between our equations. Are we going to use our constant velocity equation? Are we going to use our changing velocity equation? The other thing that's different is now some values are squared, and that's going to give us some interesting changes. Right? With proportional reasoning, and also, most importantly, constants. Anytime you have something that's not going to change, like it's a number in your equation, you don't even care about it at all when you're doing proportional reasoning. Thanks for watching.